Alrighty, so today's lesson, as I talked about in class, is very boring, right? We are today going to discuss and use the Bohr model. Okay, now it's the Bohr model of the atom. Niels Bohr came up with it. Niels Bohr's model of the atom is a strong model, and the reason that it's a strong model, it has its strengths and its weaknesses. The reason that it's strong is it gives us a two-dimensional depiction of what atoms actually look like, right? So we can get that there's a nucleus. Inside that nucleus are positively charged protons, and there are neutrally charged neutrons. And then around the outside of that, those are electrons, and those electrons are negatively charged. Now, Bohr's depiction of how this makes up an atom is actually accurate. But Bohr had a couple assumptions that were wrong as well. Those two assumptions that are wrong are this. Bohr would say that you have a nucleus, it's got protons and neutrons inside of it. And then what Bohr would also said was this, that electrons followed what he referred to as fixed paths outside of the atom. Now we know that that isn't true. We know that it's more like a cloud, and they're all over the place, and these electrons, they're moving in and out, and they're gaining, they're going from what we call a ground state, and they're jumping up to an excited state and falling back down, and we're having photons of energy being given off, all kinds of things. And so Bohr was wrong about this idea of these assumptions, that they orbited like planets around the sun. The other thing that Bohr was incorrect with his model was that he said that as you moved away from the nucleus, energy would automatically increase. Meaning, this electron here had more energy than that electron right there. Now, eventually, we're going to do something called electron configuration. And with electron configuration, we disprove that part of Bohr. In other words, this electron out here might have less energy than one that is tucked inside of it. And we're going to get a hierarchy for how we do that. And that thing's called electron configuration, and it'll happen pretty soon. Okay? But those are the two reasons why Bohr is wrong. He says that they orbit like planets around the sun. That is not right. And he also says energy increases as you move away from them. But again, we use it because, we have this two-dimensional Bohr, and I got to teach you about what an atom looks like. And it's not bad for giving an idea of protons and neutrons inside of this dense nucleus, and electrons around the outside of it, right? So I'm going to teach you how to draw a Bohr atom at this time. And the thing I'm going to use is manganese 55, or should say the element we're going to use. Now, this is called an isotope. There are multiple isotopes of manganese. Manganese can be 55, it can be 54, it can be 56. It just depends on which version of it you're using. We're going to use 55. So the first thing I recommend you do is you go and you look up the atomic number. The atomic number for manganese, and I have to look it up, is 25. So just like in the previous video, here's what you do. We count up the number of protons, neutrons, and electrons. So the atomic number tells me the protons. That is 25. There is no charge right here. You don't see a +1, a +2, a +3, anything. So therefore, it's neutral, 25 electrons. Being the positive and the negative charges, they cancel each other out. Likewise, the neutrons. We have to actually calculate them. We take the mass number 55, which is also the isotope type, and we subtract out the atomic number. So 55 minus 25, which is equal to 30 neutrons. So 25, 25, and 30. Now, Bohr's model says we take the protons and the neutrons and we put them in the middle. So we take 25 protons and we put them right here. We take 30 neutrons and we put them right here. And now we have to place electrons around the outside. There is an organization to this. Bohr says that in the first level, 2 electrons fit, followed by 8, followed by 8, 18, 18, 32, and 32. Now, one of the ways in which I remember this, guys, is that the first row, or the first period on the periodic table, has 2 elements in it, right? Hydrogen and helium. The second has 8. Then 8, 18, 18, 32, and 32. These are tough to see, but if you include the lanthanides and actinides, you get to 32 and 32. All right? So, the first level outside the nucleus contains 2 electrons. Now, one of the things you will learn later on also when we do orbitals is that this first level outside the electron only has 1 room in that house, or 1 orbital. I'm going to refer to it as rooms in a house because I think it gives you a little bit of an analogy. So, the first electron takes its own room, right? But here's the problem. I got to get to 25 of them. I've only placed 1. So, there has to be a second electron right here. All right, the second level will fit 8 more electrons. And those 8 electrons, here's how they are sorted. So 8 electrons. The first 4 will space themselves out. And actually, I did a poor job there. Okay. Notice I did something here. I'll make sure I do it right on this next one. Notice I did something here, right? I kept these electrons away from each other, and that's because like charges repel. So these negatively charged things would want to be as far away from each other as possible. So we put in 4, which is half of 8, and then they all get a roommate from there. I room them 1. Then I would go across and do this. Why? Because they're the opposites. They repel. Then if I come over here, I would come over here last. Total, we have 10. We need 25, so we got to keep going. 8 more. So 1, 2, because I did them away from each other, like charges repel. 3, and 4. Likewise, that would get us to 14. We need 25. Oh, they're getting roomies. So 6, 7, and 8. Total right now we have 2 plus 8 is 18, plus another 8, or sorry, 2 plus 8 for 10, plus another 8 for 18. But we got to get 25. All right, but we got to get to 25, right? And there's going to be some noise in the background outside, but the school day has just ended, so. We got to get to 25, right? We've got 18 in our drawing right now, so we have to place 7 more. Well, we've done the 2, we've done the 8, we've done the 8. 18. Half of 18 is 9. So in this next level, there is space for 9 orbitals. Well, that means 9 electrons could have their own room. But we only need 7 of them, right? So here's what we do on this last level. By the way, these electrons that are found the furthest from the nucleus have a name, right? Their name is they are valence electrons. There are 7 valence electrons here. Why? Because we've already placed 18 of them. We have 7 more to go. So what you do is 9 would fit. You take the 7 and you space them the best that you can, right? I mean, I'm not going to be perfect about it. I'll do my best I can. 1, 2, I think of it like a clock, and I try to space things as if it was a full clock. 3, 4, 5, 6, and 7. Again, I did the best that I could. Is it perfect? No. Are they perfectly repelling, following Coulomb's law? No, but it's a pretty good drawing. So, or I think it's pretty accurate. So that's 7 electrons in the valence shell. And that is the Bohr model for manganese 55.